problem 2 is very closely related to problem 1. I was afraid to add it up. I was going to do it all in one video, but I was running out of time because I don't think I'm allowed by YouTube to upload something over 15 minutes. But, well, I used to be able to. I can't do that anymore. For this one, all you have to do is find the location where you can apply load of length L on 2 and height W such that it will generate the maximum force in your shear diagram. What we're really looking for is which part of my shear diagram of length L on 2 has the largest area. So in this case, for example, this length is L on 2. So this one has this length here is L on 4. The only portion that can fit this whole load and still be on the same sign is this region here. So I would take the whole area. What do I mean by that? I mean literally that. Like just find the area of this and multiply it by W. And what does that actually represent? Before in our lab, we were looking at influence lines for point loads, right? So let's say that, for example, let's say that I had a graph like this, right? This was my VB. This means that if I have a load at this point, a load P, I'll have a reaction at B of 3/2 P. In other words, I just multiply the value of my influence line diagram by my load to get the value to get my reaction at B. Same thing here. I'm multiplying the height of the value of my influence line diagram by the load. But I have a distributed load. Distributed load has infinitely many points on here. How do we deal with infinitely many points? We integrate. Integration is just finding the area. So to model an infinitely many points along here, I just find the area of this and multiply it by W. And 1 times L on 2 times W. Therefore, the largest Vx I can possibly get for this diagram is WL on 2. So this is a little bit of a fine point. There are scenarios where you wouldn't normally you try to put the centroid of your load at the peak. So for example, in this scenario, I would not put my load here. Instead, I would put my load here. I would want to cover this area. Not this area, right? Because you can see here, like this one, over here I have basically 0 at this point. Here the smallest value I have is like 1/2 the height. So that's a little bit of a fine point. I feel like I'm not explaining that clearly, but if you have any questions on that, please stop by and see one of us, and we can go over that in a little bit more detail, because I think, yeah, I need to interact with you guys more in order to be able to describe this better, or interact with you guys in person. So if you have questions on this, I could probably explain it better if I can see exactly the problem that you're having. But yeah, let us know if you have any questions on how to do number 2. Number 2 is not meant to be particularly tricky. It really is just finding the area of maximum width L on 2 that gives you the largest area, or finding the section or diagram that has length L on 2 that gives you the largest area. So again, let us know if you have any questions.